This is geometry lesson 1.5. We'll be talking about postulates for points and lines. So you probably don't know that word postulate, so we're going to go over what that means and apply it specifically to points and lines, which we've been talking about as the basics of geometry. So the big idea today says that the point line plane postulate, which we'll talk about, specifically for Euclidean geometry, we've talked about different types of geometry, includes rules that the undefined terms point, line, and plane must obey, and is the basis for deduction of properties of figures. So lots of complicated words there, but we will sort through that here as we go. So postulates. Basically, you need to know that a postulate is an assumption. That's the number one thing that you want to know from. So the definition pretty much from the book says assumptions that serve as a starting point for logically deducing or proving other statements. So again, that sounds super complicated. So it's basically something that we can assume to be true and that helps us prove other statements are true as well. So it's an assumption that we make about points or lines, things that we know are true in a way, that help us come up with other theories that are true. And so a theorem is the other word we're going to talk about. And that's going to be a statement that we can prove. And we're going to use the assumptions that we already know to prove these other statements to be true. And so if you take a look at the two things that we're going to talk about here below, one is called a postulate, so things that we can assume to be true, and then one's called a theorem. So using our postulate, what can we also prove to be true? And so referring back to the big idea, the point, line, plane postulate has a couple different points here to talk about. The first one is called your unique line assumption. Again, these are assumptions, things that we can assume to be true. It says, and again, this is just for Euclidean geometry. We've talked about the other ones, graph theory and discrete. So in unique line assumption, through any 2 points, there's exactly one line. Okay, think about why that's not true for graph theory. We had those 2 points, and we could make all of those arcs go whichever way. And so through these points, you could have as many arcs as you want. Okay, but in Euclidean geometry, we're putting lines on a coordinate grid. Through any 2 points, there's only one line. Okay, and if the 2 points are in a plane, so we talked about, think about the plane as a flat space, right? It's two-dimensional. The line containing them is also in the plane. So if 2 points are in a plane, so think about this plane as the piece of paper. If you've got 2 points on it, that's on the plane, if you connected them with a line, that line is also on the plane. It doesn't go above it or below it. It would stay on the plane the entire time. Okay, the next assumption that we can make here with this postulate, the number line assumption, every line is a set of points that can be put into a one-to-one correspondence with real numbers. And so you can see here the basics. Any line can be made into a number line, and that's because every point on that line has a value, and you can count up and you can count down from it. Let's go back up here. I put this picture here for a reason. So we've got 3 letters here. That's a script L. If you wanted to enlarge it, it's a script L is what that is. And very often you'll see that as the designation for a line. They'll call it line L, and they just use L because that's what line starts with. And you'll see those written in script when they're naming the line. That is not a point on the line. There's no point up here that's L. The only 2 points on this line that are labeled are A and B. We can name this line, line L. A couple other ways that you can name a line is by using any 2 points on it. So we can call this line AB, and what we do is you put the arrows above it to show that it's a line. It goes forever in both directions. We will talk about other things that have an endpoint, line segments, rays, and they'll have a different designation up here. So this is line AB, and you can go any direction, and if there were more points here, you could use any 2 points, but you could call this line BA as well. All of these are good names for this line. They're all good names for this line. Let's get some better focus there. All right, and last part of this postulate. If we're talking about things that are 1D or 2D or 3D, there's things that we can assume. So if something is one-dimensional, like a line, it has a length, but it doesn't have a width, or it has a height and it doesn't have a width. Okay, one-dimensional. We know if it's one-dimensional, there's at least 2 points that exist in space. If it's 1 point, right, just a point, it doesn't have any dimensions. But if we have at least 2 points, there's always a line that connects it, and that's one-dimensional. So we can assume if something is 1D, there are at least 2 points. Okay, how about two-dimensional? Let's think about what does two-dimensional look like. That's like a piece of paper. I can measure it from left to right, and I can measure it top to bottom. It doesn't come up. It's a plane. So given a line in a plane, there's at least 1 point, and that should be point, in the plane that is not on the line. So if we have this line, if it's just a line and every point is on that line, that's one-dimensional. But if I have this line, and then there's a point over here that's still in this plane, that now makes this plane two-dimensional. Okay, because it has the line, but then it has something off of the line. That's two-dimensional. And then three-dimensional, given a plane in space, there's at least 1 point in space that's not on the plane. So I've got this flat piece of paper as the plane. By itself, it's two-dimensional. If I now have a point that's above it, not actually on the paper, above it, and I have connections to that, I start to now make a three-dimensional shape. So if everything's on the plane, on the flat piece of paper, and it's connected, that's only two-dimensional. As soon as I raise a point up off of the plane and everything's connected, I now have three-dimensional. So that's kind of further just defining those, as we talked about in 1.4, but those are the assumptions that we can make. And again, assumptions are called postulates. Okay, now from that, we have a theorem, a line intersection theorem. So that's something that we can prove. It says two different lines intersect at most at 1 point. And again, remember, this is Euclidean geometry. All right, if we have graph theory, things like that, they follow a different set of rules. So for Euclidean geometry, again, on a coordinate plane, two lines intersect at most at 1 point. If you have a line and it's on a graph and another line intersects it, they're never going to intersect again. It doesn't swoop back. Again, we saw that in graph theory. It could come back, it could curve. But we're talking about Euclidean geometry. Two different lines intersect at most at 1 point. And not every line is going to intersect. Parallel lines, which you've obviously studied before, they don't intersect at all. And so let's move on to them now. How can we define parallel lines? You may know what they are and can explain them, but let's relate it now specifically to the things we've been talking about. So they're two coplanar, they're on the same plane that have no points in common. So in general, we talk about parallel lines like railroad tracks. They're going to run side by side. They're never going to intersect. One thing that is important to note here is they can be identical. And so to just say that they don't intersect is not a full definition, because you could have two lines that sit on top of each other, and those would be considered parallel. And so when you really break it down, parallel lines have the same slope. Okay, they're going to go up or down at the same rate. They might run next to each other, or they can run right on top of each other. This is the designation for parallel. This says M, and we would consider this a line. Line M is parallel to line N. Line M is parallel to line N. That's what that's saying right there. Now they have to be coplanar for this to be true, right? If they're lying on the same plane and they have the same slope, they're never going to intersect. If we were on two separate planes, let's say we had a plane here and then above it there's another plane up here, and I looked at it from up above, it could look like they're crossing, but they're not actually intersecting because one's on a separate plane from the other. But if they're on the same plane, they can intersect just once. All right, so if we're given two equations of a line, different lines, and we want to know where do they intersect, we're going to just solve the system of equations. So we've already been kind of working on this a little bit and practicing this. So if we're going to solve this system of equations, we've got a couple different options. There's the substitution method. There's the elimination method. All right. Now in this case, if we're going to add these straight down and have something eliminate, we need these x coefficients or y coefficients to be opposites of each other, like a 3 and a -3, or -4 and a +4. Those will end up canceling each other out. Currently, we don't have that. So if we just start adding straight down, it's not going to work out for us. So what we need to do is multiply these by something that's going to create opposites. Sometimes you can just multiply one of these equations and not both of them to create something. So if I could somehow multiply this and create a -6, it would cancel with this one, and I don't have to then multiply the second equation by something. But in this case, I can't make a 3 or 5 or a 4 or 6 multiplying with whole numbers. Now you could multiply by decimals, of course, but we want to keep things whole numbers here. So what we're going to do is I'm going to multiply these two equations by each other's coefficients. So this one by a 5 and this one by a 3. And when I do that, I'm going to end up with a 15 in both spots. The 5 times 3 is 15. The 3 times the 5 is 15. The other ones will not match, but that's okay. The x's will cancel out, and then I can solve for y. Now, I need to make sure they're opposites. Right now, if I just multiplied, I'd end up with a +15 and a +15, and those don't cancel. I would add them and I'd get 30, 15 plus 15. So one of these needs to create a -15. So I'll put the negative there. You could put it here. You also could choose to work over here with the y's. I'm not going to, but you could. You could multiply them by each other. So this one by 6 and this one by 4. One's already negative, and so you wouldn't even have to worry about changing one to a negative. And if you found this example in the book, they actually multiply this one by 3 and this one by 2. This by 3 gets a -12. This by 2 gets +12. And that will also work. So there's lots of different ways to accomplish this same goal. I think just to keep it simple though, take the two coefficients you see, that's what you're multiplying them by, and then make sure one turns negative if you need to. All right, let's run through it. Everything gets multiplied. So 5 times the 3 is 15x. 5 times the -4 is -20y. 5 times -17 is -85. Bottom. -3 times 5 is -15x, and that's what we wanted. The reason we chose these numbers was to create this right here. 15 and -15 will cancel each other out. So let's finish out the rest. Don't forget to multiply everything by this number. So I'm going to get -18y, and I'm going to get +9. Now I can combine these. Be careful with your negatives. That's -38y. Combine, that's -76. You would divide by -38. And y equals negative, and a negative is a +2. Now I'm not done. All I've done is found what y equals. We're trying to find the coordinates where these lines intersect. Where are they equal to each other? So we know the y coordinate now is 2. We've done this before. You go back and plug in 2 for y and solve for x. So I'm going to go ahead and take my first equation here. And if you wanted to plug directly in this first step, you could. I'm just writing it out once so you can clearly see what's going on. Make sure you put it in for y, not for x. It's y equals 2. So the y becomes 2. Run that out. 3x stays. This becomes -8. And solve the equation. Add 8 to both sides. 3x remains. We get a -9. Divide by 3. X equals -3. And again, we're trying to find the coordinate, so we're going to express our final answer here as a coordinate. Remember, it's x comma y. So the x value is -3, and the y value is 2. So if I put these on a graph, I would see that they cross at this point, -3, +2. All right, let's take a look at another one that's set up a little bit differently. So this one is set up better for a substitution method here. So you could go ahead and multiply and try and stack things up and cancel. It will work. But what you may want to try is the substitution method, which says, hey, if I know y equals 3, I'm allowed to plug it in for y. Y doesn't equal 3 by itself. Y equals this whole thing. So since y equals this whole thing, I can come to the other equation and change y to this because I've already said it's equal to that. Just like if I said y equals 5, you could come to this equation and plug in 5 for y. It doesn't say that though. It says y is equal to this whole thing. So this whole thing can be plugged in for y. So I'm taking this equation and I'm changing y into what it's equal to, 3x minus 7. I still have negative 2x plus 13 on this side. Okay, all I gotta do is solve this equation. Now when you have an x on both sides, you can eliminate it either way. You could minus 3x from both sides, or you could add 2x since it's negative. I would say the best rule of thumb here is to get rid of the smaller of the two coefficients, and that will always keep your equations positive more often than not. So since this is a negative 2, I'm going to add 2x to eliminate this, and now I've created a positive 5x. If I had minus 3x, I would end up with a negative 5x. We tend to make more mistakes with negatives, so if you can keep things positive, that's great. So I got rid of this because negative 2 is smaller than positive 3, but either way will work. All right, I'm going to add 7 to get rid of it. 5x equals 20, divide by 5, x equals 4. Process is the same to go find the other value. So I'm going to go back up and I'm going to plug in. So I'll take the first one. You can use either one. Plugging in for x. Y equals 3 times 4 minus 7. That's 12 minus 7. So y equals 5. Again, the final answer is the coordinate. And so that is x comma y, 4 comma 5. That is where those lines will intersect. So this is the substitution method. If they're both set up in y equals form, substitution method is probably the easier way to do it. Okay, so number 3. This one doesn't say find where they cross. It asks you, are these lines parallel? So what we're going to do is we're going to go ahead and see if they cross. We're going to go ahead and try and set this up. So y equals x plus 2, which means I can plug it in for y. So I put in x plus 2 for y, and that equals x plus 4. I've got an x on both sides, so if I want to eliminate one of them, I'm going to minus it. That'll cancel this one out. I'm left with 2. This one also cancels. I'm left with 4. And there's nothing else for me to do. This is not true, which means since I ended up with an equation that's not true, these lines are never equal to each other. They will never cross, which means yes, these are parallel. It says, are these lines parallel? Yes, they're parallel. Another way to see it is to look at the slope. All right, if they have the same slope, notice the slope here is 1. It's in y equals form, easy to see the slope. I can go ahead and assume that these are parallel. That's a good assumption because they're going up at the same rate. They're either the same line or they're running right next to each other with the same slope. So you can identify it with slope, but these equations may not be in y equals form where you can easily see that. So you're going to go ahead and solve the equation. If your x's and y's completely eliminate and you have something that's not true, that means they never cross. If it was to say something like 4 equals 4, that means you've got lines that are actually the same line and they lie on top of each other and they also would be parallel. So basically if these eliminate like that, we know that we're dealing with parallel lines.